So in the last lecture, we saw refraction from curved surface, and today we are going to see something called lens. So what is lens? I have given the definition in
Sir, we were going to
first.
start thin lens.
Pardon?
Thin lens.
Yeah, we'll come to the thin lens, of course.
Oh.
So what is lens? So any transparent media bounded by any number of surfaces will act as lens if one of the refracting surface is curved. So lens is just a name given to a certain geometrical configuration. So at least one of the refracting surface should be curved, then we call it lens. The other surface we have no criteria, like it could be any flat, zigzag, I mean it could be any shape. So if I take a prism, a thin prism, kind of if I make this one of the side as curved like this. So even if I draw something like this, it is a lens if the light is going this way. The only condition is that one of the surface must be curved. The other may be flat, may be curved, doesn't matter. So that is the whole idea of a lens. So now we have something called convex lens. What is convex lens? What is convex lens? A lens whose
With curved surface bulging outwards.
no, nothing like that. A lens whose edges are thinner than its center. A lens whose edges are thinner than its center is called convex lens. So let's say if I draw something like this. So if I make a shape like this, then you can see the edges are thinner and the center is thicker, the thick side. So this is called plano convex lens because one surface is plane, so we call plano convex. We can draw something like this. So if I draw something like this, again you can see the center is thicker, edge is thinner. So what we can name it? This is called concave convex lens. Because eventually it is convex, but you can see one surface is curving inside, caving inside. So this is called concave convex lens. The only rule is the center is thicker, edge is thinner. That's it. If you see other thing, then you will get confused. Then if I draw two different circle, and if I believe this is the lens, so you can see both surfaces are curved and bulging outside on the other side. So what we call it? This is called biconvex. So it is convex on both sides. I can remove the part which you are. And the last category is if you take identical sphere and if you think of a cross section. So if we have something like this, so what is the name of this? Can you guess? So this is called equiconvex. So equi means that the curvatures are equal. So you can say every equiconvex lens is biconvex, but biconvex we use when the curvatures are different, and equi we use when it is same. So technically, and if you look carefully, the only thing common is that center is thicker, edges is thinner. Understood? I hope you can see this. Okay. So now I can. This is R. If I choose the light ray coming from this side, then the surface that it will hit first is called R1, and surface it will hit second is called R2. So here R1 is, if you can see carefully, if I extend this curve, it will be on the center, will be on the right hand side. And because the first surface will have center on the right, which is in the direction of incident ray, therefore R1 is positive. And R2 is flat surface, so it is infinity. And if since it is infinite, so we will not take any sign. It doesn't matter. In this case, we have R1 and R2. And if you look at the incident ray, both will have curvature on the left. So incident ray is towards the right and curvature is on the left. So beginning from the O, which we call optical center, if you move either left or if you move either right. So if you move left, it is negative. If you move right, it is positive. So here R1 R2 will have which sign? Plus or minus?
Sir, can you repeat?
So R1 negative, R2 positive.
How you decide the positive negative? You have to look
Sir,
at the
can you
center.
repeat again?
For
R1
this
is
lens, the curvature is shown to you. Can you guess the center location? Is it on the
yeah,
left or right?
side, left
Hmm?
side, left side.
Both will have left, and the light ray
Yeah,
is going right side.
towards the right. So both are negative.
So both are negative. So when you substitute the value, you have to put a minus sign, depending on the light ray direction. And if we come to the biconvex lens, then R1 will have which
R1
sign?
greater than 0, R2 less than 0.
And here
Same.
we have R, but sign will be different.
Greater than less.
So the only difference is here R and R. The rest we have R1, R2, R1, R2, R1, R2. So only for equiconvex lens, the R1, R2 are same. Okay. So that is your convex lens, and the way to understand this, you have to look at the center and look at the. So this shape is not convex. This is not convex. Okay. If I do something like this, I mean, just to confuse you. Which lens is this? Concave, convex.
Concave or convex.
Yeah, so it is still convex because center is still thicker than the edges. So when you go to optician and if you are wearing glasses, if anyone is wearing glasses, if you touch it, so most of you will have the myopia, I think, and therefore if you touch it, the center will appear thinner, edges will be thicker. If you look from the side way, so the way of looking at lens is not the front side. We look the edge side. So we look the side way, I mean the side view, and we see whether it is thicker or thinner. And you can easily see that most of the lens that uh, student at your age wears because they have myopia mostly. So they wear the concave lens, and in concave lens, the center is thin and the edge is thick. That is how we identify. So we don't see the front and back. So now we have the concave lens. So what is concave lens? If edges are thicker than its center. That is the only rule. If edges are thicker than its center, we call concave. Now, converging, diverging is the phenomena associated with the light. Convex, concave is the phenomena which is a geometrical property. So, which kind of lens is called concave and convex? It depends on the geometry. But whether it is converging or diverging, it depends on the medium property. Okay. So, for example, if I draw something like this, imagine. Imagine a medium like this. Now the cavity which I have left, which is not filled, will act as which lens? Is it convex or concave?
Concave.
Yeah, so as a lens, it is concave. But if I ask you whether it is converging or diverging, so what do you think? It is converging or diverging?
No, diverging.
So concave are generally diverging, but this is converging. Why? Because in this lens, the lens is having the
Medium.
lesser refractive index than the medium cell, the surrounding medium. So if you think this as a lens,
So it depends on the geometry or medium.
yeah,
Converging.
correct. Converging and diverging are property which is based on geometry and the medium cell. I mean, you need to know what kind of medium we have. The surrounding medium is also important. So it means the relative medium and the shape together will decide the converging or diverging nature. So this is converging lens. I mean, it will flip its role actually. Okay, if you flip the mu value, it will also flip the role. So visibly diverging will act as converging because you are flipping the role in which the refractive index of the lens and the medium is more than lens. So if the surrounding is more than the lens itself, the roles are flipped. You can think this way. So if you expect a converging, it will do the diverging and vice versa. If I draw a convex cavity, so imagine if we have a convex cavity. Let's say I fill the water. This is mu, this is mu medium, and if I assume medium is more than mu, then this will act as which lens? Now, typically it acts as converging when the surrounding is air, or if the surrounding having the Ri less than its value. But if I reverse the mu value, the role will be flipped. So now it will act as diverging lens. So if you ask me, this is this is convex lens, diverging lens. This is concave lens and converge. So the criteria are very different. I mean, you need to understand that it is not as simple as we believe that every convex is converging, every concave is diverging. This is what we studied in class 10th, but there it was default, the surrounding was taken as air and medium was denser than the surrounding. So by flipping the role, we can change the behavior also. So this is what you can achieve easily. So similar to the previous case, if I do something like this, if I draw something like this, so this lens you can see clearly the center is thinner, edges are thicker, and one of the surface flats, what I can say, this is plano. This is plano concave lens. Okay. The next variety you can think is Sorry, guys. So if I draw something like this, hmm, not going to work. So which kind of lens is this? What you can call? Can you guess? This is your convex to concave.
Convex or concave.
So at the end it is concave, but you can see both surfaces are curved outside in a way. So it's convex to concave. Plano, convex. So the next will be obvious. You can guess easily. So so again, you can call this as biconcave, similar to what we did. But it looks almost similar. Yeah, this is biconcave, and the last will be and this is your equiconcave. Okay, so same thing. If I choose the light rate coming this way, then R1, R2. R2 is infinity. What is the sign of R1? Plus or minus?
Negative.
R1, R2.
R1 positive, R2 positive.
R1, R2.
R1 negative, R2 positive.
R,
R
R,
negative, R positive.
R.
R negative, R positive.
Very good. So that is the only thing that you need to know. Okay. Now, of course, this is the lens. We studied thin lens for a reason. And the reason is we have solved the double refraction question in the last lecture, in which the image formed by the first surface is the object for the other, but because of thickness, what we realized that the object distance we have to recalculate. Okay, if it is thick, then if two surfaces are far apart, the problem is we have to recalculate the object distance for each surface. If I make it really thin, if the gap is tending to zero, technically very small compared to the image position or the object position, you can say. So image of the first lens will be exactly the object of the second. I mean, there is no need to modify the position because of the thickness is tending to zero. So the idea of thin lens is to make sure that the calculations are quite easier. It is not like we cannot solve the question if it is thick. You have to just do the refraction from curved surface. How many times? Two times.
Two
Two
times.
times.
That is the problem with the thick lens. So every lens which is thick, we have to solve using the refraction law. But the benefit is the moment I make the lens thin, the refracting surfaces are assumed to be almost at the same position, slightly here and there. And that will give you a flexibility of getting the answer much faster, much better, and much easier. And that will lead to a generation of some new formula which you call lens formula and so on, or the lens maker formula. So we'll see that how a new formula is derived when the lens is thin. Okay. So definitely the derivation of formula is only meant for thin lens, because when I say formula, then thin lens will offer you some sort of formula, but if it's thick lens, there is no formula for that. For every question, you have to derive it separately. That is the difference. Now, when I say thin lens, then these all pictures are misleading. These are thick lens, quite a thickness. Only the contact lenses are thin lens. Okay, so if someone is wearing the contact lens, if you have seen the contact lens, you can imagine that is called the thin lens. Okay, and the benefit is contact lens, although very thin, but it is having the center thicker, edge thinner, or vice versa. That is small changes in thickness is doing the job gracefully. Okay, so you can understand that how by changing the curvature we can achieve the desired bending of light. Because at the end of the this entire chapter, the only purpose that we serve is to bend the light. If you remember, in the very beginning, I said, what is the whole purpose of geometrical optics? The answer is to bend light. So when human eye is not capable of bending light sufficiently to focus on a retina, we take some help from the auxiliary bending instrument, which we call lens. That's it. And lenses are designed in a way that, okay, they offer you sufficient bending property. So with the aid of lens, we can focus the same light ray on the retina and will make the objects visible. Okay. So lenses, when you wear lenses or glasses, it's called aid. You aid your eye. So lens is, or wearing glasses is not a disease. Okay. This is not at all a disease. It's just like the God has given you a different curvature. The God has given you a different refractive index, and therefore it cannot be done. If it is most of the genetic disease, if it is eye related, it is the evolution process. I mean, problem, you can say. So the way you have been evolved, your ancestors, they have different eye shape. So that is called genetic problem. There are some problem which is arising due to the change of medium, the aqueous humor, vitreous humor inside the eye. And the aqueous humor, vitreous humor will have different refractive index, and with age it will change the value. So by using some chemical, we try to balance its RI value. So only those are curable which can, which is related to the mu, the refractive index. If it is related to the curvature of eye, it is not removable. I mean, you need to wear a glass for sure. Nowadays, with some technological LASIK technology, they change the curvature of eye also. I mean, of course, they are doing it, and how they're doing it, I'm not in complete idea of that, but they are doing it somehow. I have heard that okay, they can change the curvature also. So even the genetic problem can be removed with some advanced technology. Okay. So classically, we say that the RI problems can be removed with the help of chemical. You have some eye drop, you put it, it will change the aqueous humor RI value or vitreous humor, and then the focusing of light will be as usual, the way it should be, and we can see it better. Anyway, so thin means really thin. I mean, thin need not to be like this is very thick actually. This, if I go by the representation, these are very thick lenses, extremely thick. I mean, thin is like contact lenses. Okay, so that's why when you wear a glass, okay, the glass having the problem that the glass, if someone is wearing, then the gap. Okay, so if so anyone wearing the glass, the eye position is slightly behind, right? And there is a gap here. And this gap again will have there are multiple refractions. So refraction here, then refraction on the other side of the same lens. Then it will travel for some time, then again refraction, again refraction. Contact lens will have lesser refraction. So it is easier to kind of manipulate the thing in case of contact lens. Yeah. So contact lens is better for the image formation than the regular lens. That's why it is expensive also. You need to pay a lot if you want to have the contact lens. It means it's not very expensive in that way. It's affordable, but for a normal human being in living in India, in villages, they cannot afford. Okay, the maintenance is expensive, and they are not doing some very precise work, so they are doing the work which can be manageable normal glasses. And you see the difference of vision. So we have to derive something called lens maker formula. See, there is no formula for lens. We have only formula for refraction or reflection. So when you say that for lens formula or something, you're trying to apply the Snell's law on the two surface of the same lens, and in a way you are manipulating and converting into a formula, and you're calling it a formula. So I'll start with a simple convex lens to derivation purpose. Just remove this. To make it thin. If I make it really thin, it is difficult to understand. But this is better. Thin and good. Okay, so now to find the, and what we'll do is, while deriving the formula, we'll assume the medium is not just air. Let's call the medium is having some value. So we have kept the lens in an isotropic medium. A lens kept in isotropic medium. So because the medium is isotropic, it means no matter which direction you go, the property of medium is same. So I will assume that mu is same. So mu is same on both sides. Then the lens maker formula is derived. And then the lens formula is also derived. So lens maker formula or lens formula is a formula that is only applicable under the assumption that it is kept in isotropic medium. If it is kept in a multiple medium, let's say if it is on the left, we have medium 1, on the right, we have medium 2, we cannot derive a formula. Then we can have, of course, a simple a formula, but that won't be called lens maker. The other assumption is thin lens. So we are going to have 4 thin lens. What is the purpose of thin lens? Just to make sure that the answer of the result of the first surface is exactly the object of second without modification. I mean, the gap will not affect the answer. If you remember in the last lecture, we had a sphere and the image formed by this surface was the something here. Then for this surface, because it's quite away from the first surface by 2r, the V1 and the U1 got shifted, right? If you remember the answer. Now, if it is really thin, then the image formed by the first surface will be here. It will go out of the lens for sure. And the distance of the first image from the second surface is same as the answer, isn't it? So this gap is nothing. Do you realize this thickness idea?
Yes, sir.
So thin lens will offer you this flexibility, nothing else. I mean, this is the only purpose of thin lens. But to derive any formula, I mean, of course, thin lens won't be sufficient. So the only formula we have is the formula of refraction from curved surface. So let's say the mu of lens is mu. We can call mu L. So refractive index is mu L and the medium is mu M. Please look carefully that when I derive some formula, I have some assumption. If the assumptions are not met, you're not supposed to use the formula. If it is thick, don't use the formula. If the mu is different on both sides, don't use the formula. Every formula in ray optics, whenever we are deriving, there was some set conditions that the rays are pixel, things are like this or that. Whenever the domain, the scope of a derivation is given to you, and if a problem appears beyond the scope, it means you have to go through the basic. And what is basic? The basic is 2 things only in physics. I mean, in ray optics, reflection, law of reflection, and law of refraction. There is nothing more than that in entire ray optics. Okay, that's simple. But every formula that we are deriving is under some scope, under some condition. And while solving also, we look for similar scope. If the scopes are not met, we never think of applying the formula. For example, if I give you some very famous example, which you will come across for sure in future. So there's a thin lens. Definitely it's a thin lens. That's called, this is thin lens. And this is air, this is water, and this is mu L. Can we apply the lens maker formula or thin lens formula or lens formula here? The problem is the lens is not kept in isotropic medium. We have left air, we have right water. So this condition is not met. So whatever we are going to derive here, we cannot apply for this question. And therefore, this question becomes the primary question, like the first principle problem. Okay. First principle means you have to apply the basic and derive the answer using the basic law of refraction. Of course, we are going to use the paraxial rays, so it means we can use the refraction from curved surface formula. But what we can use and what we cannot use, that distinction should be born in the mind of the problem solver. If you miss that scope, probably there is a high chance you will commit mistake in solving question. Okay. Anyway, so this example will serve you as a deterrent that what not to do more than what to do.
So for this, we have to use what we were doing in the last lecture.
Yeah, exactly. Correct. So you have to use the reflection from this surface. And because it is thin lens, so you can take the image of the first as the object of the second, but to use the reflection again here. So what you can use, because thin, so the V1 will act as V2, I mean O1, you can say the object of the second surface. And then you have to again use the reflection from curved surface to get the final position. So we'll see this question. In fact, we will solve this question. But right now we are trying to derive the formula, the lens maker formula. What is lens maker formula? A lens kept in isotropic media. So, so, oh, so how to write the reflection from first surface? If the object is on the left, how to write? So you write mu2. So first surface, for first surface, what is mu2? It is air, it is mu, right? For first surface. And someone solving question for second surface will see mu m, sorry, this is mu m and mu l. Do you realize this? There are two curved surfaces.
Yes, sir.
So how we are going to write the equation? So I'll write on the next page. And we are deriving the formula in general, so we are not going to put any sign. So how we write mu2 by v, mu1 by u equals to mu2 minus mu1 by r. So let's write down this formula. So for first surface, the second medium is length mu l by v1. Why v1? Because this is not the final image. So this is called the intermediate image. Because one more reflection, it has to suffer for sure. What is the mu1? Mu medium. What is u? So let's write u. We don't know plus minus whatever. So we just write u as a symbol. Then mu2 minus mu1 by r1. Again, I'm not writing any sign because I am not trying to derive for one particular lens. We are deriving for in general. So when we solve question, then we have to think of lens given to us and then R1 R2 sign. Right now we are just starting R1. Okay. Now the V1 will act as the object for the second surface. So for second surface, what is the second medium? Tell me.
Mu m by v1.
V
No, v. Sorry.
final
Minus
minus
mu l by v1
V1 because it's the thin lens. That's the property. See, I
is
am not
equal
going to
to
modify
v1.
because it's thin lens equals to second minus first upon R2. Is this clear?
Yes.
And now no need to worry. Just add the equation. You will get everything. So 1
Sir,
plus
I'm
4.
getting confused with the 1 and 2, which is first, which is second.
Object is on the left side. So
Yeah,
light ray will come like this.
yeah.
So we have first surface, we have second surface. This is the first surface, second surface. So for first surface, we believe that the entire world on the right is mu L.
Yeah.
We are believing that okay, the entire world on the right is mu L, but it is abruptly ending. Na? So assuming that the right world is mu L, where the image is going to be formed, assuming it is continuing forever, where the image will be, that is your V1. Okay. But we know that very soon it will suffer some refraction.
Yeah.
So the answer which we got, assuming it is continuously present everywhere, will act as object for the second surface.
Yeah.
And then it will form the image. So I'll show you by doing a thicker. Okay, I'll show you separately once again. Don't worry. Now you got a bit. Okay. So we assume the continuation of the medium on the right side. But unfortunately, it is like if I have only one surface and if you have just R1 and this is mu medium and this is mu L, and there is like it is not ending, it is everywhere. So the answer what we got is V1. The V1 is in assumption that okay, let's say this is going this way. Now imagine suddenly the medium abruptly ends. So for second surface, this is the incident ray, and this is a virtual object. If you realize, for second surface, this is the incident ray, isn't it?
Yes, sir.
And this incident ray is converging,
Yeah.
will form the virtual object. So this object, this image will act as virtual object for the second surface, isn't it?
Yeah.
But it will suffer one more reflection. It may form image finally here. So this object will have image here.
Yeah.
That is what we are doing. Is clear now?
Yes, sir. Clear now.
So if you add the equation 1 and 2, what will get? I think the intermediate answer gets cancelled. That's the beauty of the thin lens. Every intermediate image, even if I make multiple thin lenses, let's say 3 or 4, the process remains same. The every intermediate answer will cancel out. So the addition of 1 and 2 will eliminate the intermediate value, which is mu L by V1. And what you will left with is mu M by V, mu M by U is mu L minus mu M by R1 plus mu media minus mu lens by R2. We can simplify this. 1 by V minus 1 by U. And this we can take as common as mu L minus mu M. And the other term becomes 1 negative. So 1 by R1 minus 1 by R2. And therefore 1 by V minus 1 by U becomes mu lens by mu medium minus 1 into is this formula clear?
Yes.
Yes, sir.
So this is your lens formula. Okay. So this is the formula as of now. I mean, we'll just call it lens maker formula. So this entire term is called 1 by f. That is the focal length of lens. This entire term is called focal length of lens. How we can call it like this? So we know that if u is tending to minus infinity, the v will tend to, by definition. If the light ray is coming from infinity, that is parallel to the principal axis, then wherever the image will be formed is called focus, if you remember.
Yes, sir. For
So if I substitute this answer u as minus infinity and v as fl, what will get? 1 by fl minus 1 by minus infinity, which is 0. So this is by definition. Therefore, one by fl is the entire term written here. So 1 by FL is mu medium by mu length minus 1. Oh, I made a mistake. Just mu L by mu medium minus 1. So this formula is called lens maker formula.
Sir, but why did we take at infinity, u at infinity?
Because the way we define the focal length is the same. How we define the focal length of any system? We assume the light is coming from infinity.
Yeah.
Wherever it converges, we call focus. So focus is not a geometrical property, it's a property of geometry and light both. So focus is property which you can say geometrical plus optical property. Whereas the center of curvature, radius of curvature, all are geometrical property because it's pure geometry, isn't it? So if you remember the earlier lecture, the beginning lecture, I have explained clearly that focus of focal length is having dependency on the light, not just shape. Understood? So that's the definition. Whenever if you see, whenever you ask me what is the focus, I'll take a U as minus infinity, I'll find V, and that is the answer. Understood? For any given system,
Yeah.
how to find the focus? Take the U
U
at
at
minus infinity. That's it. Assume the light ray is coming from infinity. Wherever the image will be formed is called the focus. Is this clear? So
yes, sir.
focus is also image point, but only for those objects which are at infinity. Other points are definitely having different answer for image other than focus. So 1 by FL is called this is entire term is called lens maker formula. Therefore, equation 3 implies 1 by V minus 1 by U. We can rewrite as 1 by FL. And this formula we call lens formula. Now, lens formula is only applicable when this is applicable. This is only applicable when it is thin lens. And the medium on the both sides is same. Because the way we have arrived at this equation called the lens formula is through various assumptions. You can see when we started the derivation, we assumed the medium lens is kept in isotropic medium. So first rule to apply the lens formula is the lens kept in a medium which is same on both sides? Yes or no? If it is yes, you're lucky, you can apply the lens formula, else don't apply. Understood?
Yeah.
So when you apply the lens formula depends on lens maker formula. The maker formula depends on some assumption. So everything is dependent. These are called dependent relations, and therefore they have a scope of application. They cannot be applied just like that. So you cannot take a lens and apply just like that anywhere. I hope this is clear. Okay, so
Sir, but this one, the lens formula, how did we derive that?
in the equation number 3, this entire term we proved as 1 by FL.
Oh yeah, yeah. Sorry, got it, got it.
So you just need to substitute that value. Okay.
Yeah.
Okay, so this is the lens formula. So this is what we studied in high school, right? And the way we studied there was quite different. The way we are studying here is quite different. And what you need to realize that focal length itself is not a constant property, even for paraxial is. See, this is for paraxial for sure. But what I'm saying is that even for paraxial, the answer of focal length is quite challenging. So focal length of lens depends upon what? Mu of lens, mu of surrounding medium, and geometry. So R1 R2 is geometry property. I mean, it's pure geometrical property, with whereas mu M is optical property, and therefore every light component will have different focal length. So if you think of a lens, and if you think of a white light, then in general, if it is not a paraxial ray, if it is not a paraxial ray, if it is a ray in general, and if it is a white light, then the mu as per the Cauchy's relation, which we know is a plus b by lambda square, the mu for every component of light will vary. And we know that mu is maximum for the violet and the least for the red light. Okay, you don't know anything. Okay. So if you remember in the formula, the inverse of focal length is proportional to mu L. So FL is inversely proportional to mu L, which means more the refractive index, lesser the focal length. That is why after refraction, the violet will be the nearest object or the nearest point, and the red will be the farthest. Let's change this. Uh, so the focal length of the violet and the focal length of the red will have difference. Although for paraxial, the differences are not quite visible, but there will be a difference if it is not paraxial. And this is called, we have discussed before also, it's called longitudinal chromatic aberration. Okay. So the longitudinal chromatic aberration, as you come down, we have discussed in prism also. So of course, the H will make it prominent, and as you decrease the H, it will become really close. So we will have the DF. So the LCA, called the longitudinal chromatic aberration, is actually equals to DF, you can take modulus, and therefore we know that 1 by F is mu L by mu M. So we can, if we take a mu medium as air, let's define for air. So for air, the 1 by F will have the formula mu minus upon 1 minus 1 into, so F and mu are proportional, I mean inversely proportional to each other in a way. So 1 by F is mu minus 1 into 1 by R1 minus 1 by R2. And for different component of light, R1 R2 remains same because it's geometrical properties. We can write as 1 by F equals to mu minus 1 into some constant. We can just call it constant. So the way we can write is F into mu minus 1 equals to some constant k dash, just we can cross multiply. And therefore, if we differentiate, so df by f plus d mu minus 1 by mu minus 1 is equals to 0. And this you can write as so df by f plus d of mu minus 1 by mu minus 1 equals to 0, which you can rewrite as d mu by mu minus 1 equals to 0. So d mu by mu minus 1 is minus dA by f. And if you remember, what is this? So the dispersive power, if you remember, the dispersive power is defined as mu violet minus mu red
Yes, sir.
upon yellow minus 1, which is the average.
Yes, sir.
And the mu violet and mu red we can write as d mu, and this we can write as mu minus 1 for a smaller deviation. And what else we can understand that the df is f red minus f violet, right? So d mu and df are opposite, and that's visible from here also. So what we say that the dispersive power is minus df by f, and therefore the minus df is omega into f. So the longitudinal chromatic aberration is actually product of dispersive power and the focal length for yellow light. So that is what we take the average. Okay. So omega into focal length of yellow light is called the longitudinal chromatic aberration. Is this clear? Is this clear? Yes or no?
Yes, sir.
So for thin lens, we can use this relation for longitudinal chromatic aberration, and later on we'll come to know that okay, every lens will have the chromatic aberration. So if you want to achieve a zero chromatic aberration, if you want to achieve that okay, white light should not suffer any chromatic aberration, then we use combination of lens, and we create something called the achromatic combination of lens. Okay. So there is something called achromatic, which means no aberration should occur. So one lens will always create the chromatic aberration. So if I choose two lenses of opposite property, so one may be convex, other may be concave, then the chromatic aberration of the two will have a opposite sign, and the summation may give you zero value. So that's called the achromatic combination of lenses. So let's say we have two lenses. Okay, right now I don't understand okay whether they are going to be concave or convex or combination. So let's say we have omega of the omega be the dispersive power of the omega 1, and f1 is the average focal length, which is the yellow for yellow light. The other is omega 2 and f2. So the LCA of combination, we can use the superposition principle, and that kept in contact, so there is no gap. So we can say LCA of combination is omega 1 f1 plus omega 2 f2, and we want to make this zero. So for achromatic condition, that is if you do not want the light should suffer any chromatic aberration, for achromatic combination we can say omega 1 f1 plus omega 2 f2 equals to 0, and this gives the relationship that omega 1 f1 is minus, because the dispersive power is always a positive quantity, so we can say f2 will be having the opposite sign that of the f1, right? Which means achromatic combination is achieved when we use one as concave, another as convex. I hope this is clear.
Yes, sir.
So such combination results into the achromatic combination. And when you go and buy such glasses with achromatic combination, it is generally expensive. So the achromatic combinations are a bit expensive. And these lenses are basically the goggles. If you have the goggles, they make sure that the goggles having the zero power. So goggles are used by the mostly sports person. I mean, not mostly. I mean, of course, any fashionista can use. Okay. So the omega one f1, omega two f2, and we know that the nature of the two lens must be opposite. If one is converging, other must be diverging, and vice versa to achieve the same task. All right. So this is the achromatic combination. We have all the formula that we need to solve any question now. So we're done with the most of the derivation except few in this chapter. So let's write the formula, lens maker formula. Lens makers. Let's keep it lens maker. So history of optics is very old. It is since the time of Galileo. So 1 by focal length of a lens is the relative refractive index of a lens with respect to its surrounding medium into its geometrical behavior. So if plano convex lens, plano convex lens is kept in air. So 1 by FL will be okay, plano convex. It's easy. Now, when you calculate the focal length, you have to assume the light ray. The good thing is it doesn't depend the way you assume, but you have to assume to right. Because R1 R2 will have the meaning, and what is the meaning of R1 R2? It is the first and second surface of refraction. So
Yes.
R1 is the curvature for the first surface of refraction, R2 for the second, and therefore the direction of light ray will change the R1 R2, right?
Yes.
Okay. Therefore, if a plano convex lens is kept in air, if I choose this as the light, this will have infinity, this will have some value R, and this is mu, this is air. So how to write 1 by Fn? Mu L is mu m is 1 minus 1. 1 by infinity minus 1 by minus R, right? Is this clear?
Yes. So first one is flat. So infinite.
And second one will have the left side center,
Yeah. Negative.
so negative. Imagine if someone is trying to solve the same problem and he is assuming the right ray from the right side. It really doesn't matter because for this guy, this first surface. So how to write mu by 1 minus 1? So far, so good. 1 by
Yes.
plus R minus 1 by infinity. Because the light is going left and the
Yeah.
center is also left. So it means the it is same side, so it's
Positive.
plus.
Yeah.
And therefore, it really doesn't matter how you choose the light ray, but you have to choose the light ray so that you can write better. So the final answer will be mu minus 1 by R. So the focal length of a lens, plano convex lens is mu minus 1 by R. So I can write here something like this. So what we can write here, that FL is R upon mu minus 1. So I mean, plano convex. Now, these are very typical formula that you will come across. For equiconvex, it's again very famous, equiconvex. So if you have equiconvex lens, R is going to be same. So it's like a two plano is joined together, isn't it?
Yes.
Like a two planos are joined together. You can also think as this as combination of two plano, which we will see later on that when we study about the combination of lenses. Okay. So if I choose one plano convex lens, the light will be bent by some amount. If I make it twice, the bending will become again twice.
Yeah.
So more bending will result into less focus, less focal length, right? So if the light is coming like this, we'll bending like this. So I was expecting here, now I'm getting here. So my focal length has decreased, no?
Yes, sir.
So combination of focal length will follow the inverse relation. That's why you will come to know that inverse of focal length increases because focal length decreases. Anyway, so to derive the formula here, you can use the same formula, 1 by Fn, and I'm taking by default in air. If medium will come, then I will change the answer. So 1 by Fl equals to mu minus 1, because in air we can just start mu minus 1. 1 by R, light ray, if it doesn't matter. If you choose the light ray like this, it will have 1 by plus R minus minus R, correct? Can you see that? Can you see that? Yes or no?
Yes, sir.
So 1 by FL turns out to be how much? It is 2 times mu minus 1 by R. So the FL is basically R upon. And what is interesting that if I call FL dash, it is exactly half of the FL because it is the double of the plano, right? So if you use two plano convex together, it will half the focal length. And that is, I think, logical if it is equiconvex. Because more the bending, lesser the image distance from the center of the lens, which we call optical center.
Yes, sir.
Is this clear?
Yes, sir.
Okay, what happens if we immerse the lens in media? For any lens, 1 by F air, like when it is kept in air, the answer will be mu minus 1 into K. K, why? Because change of medium will not change the K value, right? So if I take a lens and if I dip in water, the R0 remains same or change?
Sir, it will remain the same.
That's why I'm taking K. So 1 by F medium will be what? Mu L by mu medium minus 1 into K. So therefore, 1 by F air upon 1 by F medium will be what? And therefore the F medium will be how much? No need to mug up the formula, you can just write the formula once again, divide it. So for example, there is a very famous question. A lens of a refractive index 3 by 2 is immersed in water of Ri find the ratio of F medium by F air. Like compared to the air, what is the new value of focal length? Tell me the answer. What is the answer?
Sir, one sec. So 4/9.
No. So 1 by F air, if I write as 1 by F, which is 3 by 2 minus 1 into K, which is K by 2,
Yeah,
and 1 by F medium will be 3 by 2 by 4 by 3 minus 1.
yeah. Sir, I did this only.
So this is 9 by 8, which is 1 K by 8. Nine by 8 minus 1 is 1 by 8, right?
Yeah,
So K by 2 by 8 by K, which is 4.
yeah, sir. I forgot to do the -1, so I just wrote 9/8 only.
Yeah, that's the point. So what you can realize that the given length of given mu, if kept in water, its focal length becomes 4 times, which means it will travel farther before it converges. And that is logical because the second medium is not air, so it will not bend as much as it was bending before, isn't it? And if you do not want any bending, if you want that it should not bend at all, make the medium same as the length. What will happen? If the medium is same as length, what will happen? It will continue the motion. Why it will bend?
Yeah, yeah, yeah. It will
I mean,
be
there
this.
is no there is no refraction.
Yeah,
Refraction for refraction, we must have the different media.
yeah,
So in that case, the focal length becomes infinity because no lighter will bend it at all.
yeah.
Now, how to cut a lens to change the focal length? Cutting of lens on its focal length. See, by default, if I do not mention anything, it means the lens is in air and we are doing everything in air. So by default, until nothing is mentioned explicitly about the medium, you are supposed to take air. Understood?
Yeah, sir.
And this goes without saying. I mean, there is
Yeah.
nothing written anywhere in the text. You have to assume this. Okay.
Yes, sir.
So let's say if I have a lens which I cut into two halves. So lens is cut into two pieces like this. This is called the longitudinal cut. So we simply break into two pieces. That's the whole idea. While doing so, you never affect the R naught. It remains intact, right? So the reflecting surface will have the similar curvature. So K is not changing. You also do not affect the mu. So mu is also not changing. So technically, the focal length of this part and this part and the original lens that we cut all will be same. So what will change here? So what will change here?
So there will
Only
be more
aperture.
number of
Only what you
reflections.
say, the aperture will change. Aperture means the light refracting area will change. It will become half, right?
It will be less, yeah.
So when the area is half, the intensity of image will change. So if you try to create the image with a smaller portion of the lens, the only difference will be its brightness, nothing else. Okay. So if the brightness, or we call mathematically intensity of the image as formed by this is I,
So it is directly proportional to the square of aperture.
yeah, which means proportional to area actually.
Yeah, the
Aperture is the linear dimension. So if you half the aperture, so you are not changing the biggest dimension because it's a, okay, I'll come to that. So here you're cutting the half, but aperture is actually same. Unfortunately, for a circle or for a semicircle, the diameter is same, right? The biggest dimension is same. Aperture is called the biggest dimension, the linear dimension of an object.
yeah.
So here it is confused. In circle, the biggest dimension is diameter. Here it is also diameter. So aperture is essentially not changing. What is changing is the area. So now we are receiving half of the light energy, right?
Yeah.
Because only half of the energy is proceeding forward to make the image. So definitely it will be half in intensity. So we say uh, F remains same, but intensity decreases. So we have to calculate the area of refraction. I mean, through what area the light ray is passing through. Okay. So we do not affect the focal length because what we really need, if you remember the prism chapter, I told you that every part is a lens or prism. Okay. So guys, I'll take a break of 10 minutes, then I'll come back. Okay.
Okay, sir.
So you can join me after 10 minutes. I'm pausing. Hello guys, my voice audible to you?
Yes.
Okay. Okay. The next is called transverse cut. So if you have the thin lens, but if you cut it transversely, right? So the way we are going to cut is so by while doing so, what we do is we make one surface as infinity, others are. So now we have converted the equiconvex into two plano-convex, right? And the refractive index will remain mu here. So what will be the effect? If you make the equiconvex into plano-convex, the focal length will become double, right? We have seen that. So the focal length will be how much here? If this is f, then this will be, and you can prove it. We have proved this for f equiconvex is FL by 2. So FL is twice of equiconvex, right? F plano-convex is twice of F equiconvex. It's clear? Hello guys, am I audible?
Yes, sir.
This part is clear, no?
Yeah.
So whenever a equiconvex is cut into two halves, you make the focal length double. What about the intensity? So the light refracting area is same, right? Okay. So light refracting area remains same. So you can see here the amount of light if it is entering through this much area. The same can enter here also, right? So intensity of image remains same. Sorry. Now you can see that okay, I have made a sorted combination of lenses. So I've taken multiple lenses and cut their pieces and joined together. So it looks like we have multiple. I mean, we have single lens, but it is not single lens; it's multiple lens. Okay. And each color represents one refractive index. So, so you can say this is mu one. Okay. Now the purpose of showing this way is that the R1 R2 is same for every lens, right? They are part of same curvature,
Yeah.
but focal length is depending on k is same for all, but mu will change, and therefore f will change. So a single object is actually kept in front of five lenses. It's not one lens. So what you can expect is there are five different images. So one object will have how many images?
5.
Five images. So it looks like a one lens, but it is not one lens. It is five separate lenses. And what we are doing is we are taking a part of every lens and joining together, keeping the curvature shape. Now, if we have a medium, So again, every color represents a different mu. And if I go by the same logic, how many images do you expect for one of?
So 4.
Yeah, right. So every pair from here to here will have create one, right? So from here to here, we will have one value. So the light has to go through both surface. So if you take this portion, then you can see this is a different combination of mu, and this pair is again different, and this pair is again different. So we have multiple pairs, and therefore we can expect 4 images. So these were some basic concepts of lens, and also we have seen the chromatic aberration issue in case of lens. Okay. So let's go to the next concept. Sometimes when you buy or purchase a lens of big aperture size, and if you want to perform experiment in your school lab, in which you want to make sure that the rays are paraxial, the way of doing is we paint the outer periphery. So when I draw a lens like this, it is actually like a saucer plate or like a plate. This is the actual shape, right? And imagine you don't want the marginal rays to interfere in the image formation. So what you do is you keep a small circular part portion open and rest you polish. You simply polish it. Or I can make it like this. Only this portion is transparent, rest is you can see it's dark. So now what will happen? As a result of this protection, the marginal rays are totally eliminated. So to eliminate the marginal rays, we generally do this kind of trick. Now the image formation will be due to the rays passing through this small aperture, and therefore what will happen? You will get a distinct image.
Sir,
And
I didn't understand what we are doing now.
so we have a lens and we are painting it on the outer periphery. Painting by
Oh, so
black
that
color.
is the paint. Okay.
This is a like this portion is now painted by black color. So light will not go on the other side. Understood?
So we reduce the aperture.
Correct. Light refracting area. So let's say this is R, this is R. If the intensity of image was I here, what will be the intensity of image here? Well,
I by 4.
hmm?
I by 4.
I will. And if I flip it, like if I make the central part darker, that is, I will stop the light here, and the remaining part is letting the light to go through, then what will the new intensity?
3 I by 4.
Yeah. Very. So what is the takeaway here? That we need to understand that the light refracting area decides the intensity of image. So by changing the light refracting area, we can change the intensity. Understood? So instead of looking in terms of aperture, which is sometimes confusing or misleading, I would say, always think of area as a mean of intensity. Okay, because the whole idea is more the light, more the intensity. That's a simple logic as such. Okay, so if you give more area, I can let more light to pass, and therefore a better I mean brighter image will be formed. Okay. So what else we can do is lens. Some examples to understand the medium. So let's say we have a lens. A light ray is going this way. Mu1, mu2. What kind of relationship do you see here between mu1, mu2, mu3? It means what is the inequality you can see? Okay. What is the general
But
trend
it
of
will be
convex lens? It will converge, right?
Converge.
So it will try to bring the light ray towards the principal axis, right?
U1 is greater than U2.
So mu1 is more than mu2, that's for sure. Because the role has been flipped, it means the mu must be opposite. But mu2 is more than mu3 for sure. Correct?
Yes.
And because mu1 is more than mu2, mu2 is more than mu3, so luckily we have another inequality. So what do you expect the relationship here?
U2 greater than U1 and बॉल वगैरह छोड़ लेना इसमें U3 ये बदली बॉल पर छोड़ लेना
And there is no refraction on the second
Oh,
surface, it means the
yes.
mu2 mu3 are same. Okay. Okay. Imagine if we have a lens which is thin lens. We always keep thin lens because without thin lens I cannot even use the uh, lens maker formula and something like that. But here we can use nothing. So we are keeping thin for the sake of derivation, nothing more. The difference is the mu on the left is mu1, but on the right is mu. So what we cannot use? We can neither use lens maker or the lens formula, right?
Yes.
Now, here the focal length will depend on from which direction the light ray is coming. So I'm taking the light ray coming from this side. Assuming if mu is more than mu1, it will bend like this.
Yes.
And assuming if mu is more than mu2 also, it will bend like this. So if
Yes.
mu is biggest one, like more than mu1 mu2, then the light ray will converge eventually. It is also possible that the mu2 is more than mu. In that case, it will diverge. And as a result of diverging, it may go like this also. So it is also possible that a light coming from infinity can go to infinity. Everything is possible. Now, the question is, find the focal length. And the definition is simple. To find the focal length for the light ray coming from left, so we assume it's coming parallel to the principal axis, which means it is parallel to the principal axis coming from infinity. And the image formation will be the focal length, right? So wherever it will get focus is the image position, isn't it? How we solve? So we keep the R same for the sake of simplicity. So what we cannot apply? Any of the formula we derive. So we have to apply the basic. We can write as for first refraction,
So we are deriving the general formula.
yeah. So tell me the first reflection what we have tried, which mu2 by v minus mu1 by, right?
It's nu by v
v1
minus v1 minus nu1 by u is equal to nu minus nu1 upon v.
plus or minus, that is plus r, no?
Yeah, plus 1.
And the u is infinity.
Yes.
Okay, anyway, for second,
Nu2 by v minus
now because I have taken u as infinity, the v becomes f.
f minus nu by v1 is equal to nu2 minus nu over minus 1.
And the next step is just add this because we will always add to cancel the intimate value. So mu2 by f equals to how much? I can add like this after, and then you can take r as. So you can see the if the light ray is coming from the left side, it is mu2 by f. We are getting this much. And if the light ray coming parallel to the principal axis goes to infinity, which means if the f is infinity, f is how much? If f tends to infinity, it means there is no deviation. This is called the no deviation condition. So f will be infinite only when the denominator is 0. And that is a very powerful formula that if the mu is average of the two on the right and left, and if mu is the average, it means it is more than the lesser and less than the more bigger value, right? So whenever this condition is satisfied, then the light ray will suffer no deviation. It will bend for a bit and will may have some lateral shift because of the thickness, but that shift will be almost negligible, and we can say it will just go straight. Understood? So you won't be able to see the lateral shift because of the thickness is thin. And when we say thin lens, it means it is millimeter thin. Is this clear? Do you realize why this is happening?
Yes, sir.
So for no deviation, the mu is let's say more than mu1. So what will happen? Light will bend down. But the mu2 is more than mu, so it will bend away from that and eventually becomes straight. Okay. And if mu is more than both, it means it cannot be equal to average, isn't it? In that case, it will only bend, and you get some answer. Similarly, if I Now, if I change the side of the light ray, if I change the side, let's say light ray is coming from right, the answer will change. The mu2 becomes mu1. The rest will remain same. Okay. Okay. And if you remember, I gave you a question in the very beginning that if we have water, let's say, and we insert a lens, thin lens. So definitely we cannot apply the formula, but we can apply the lens maker formula as many times as we wish. Sorry, refraction formula. So this is, let's say, mu lens is 3/2 is fine. Mu water, let's call it 4/3. The radius, it is equiconvex, so I will take just r as 30 centimeter, and the object is here. Uh, okay.
Medium one is
Yeah, medium one is it. I'll take this length as how much? Let's take 80 centimeter. That's too far. Find the image position.
still cannot show a previous page. Not also. So while writing the you have to take minus it, right?
Pardon?
While writing we have to write minus it.
Yeah, of course. When values are given and when you're
So I'm
substituting the value
getting
of a
minus negative value.
that's fine.
It's minus 96 something.
Okay. So first of all, mu2.
Sir, can you wait for only 1 minute, please? Yeah, sir, I also got,
How much?
sir, I got minus 29.
And let me check. Mu2 by v1 minus mu1 by u mu2 minus sorry, yeah, minus 1 by r. For second surface, mu by v mu1 by v1 uh, final minus upon minus we can add it 4 by 3b plus 1 by 80 and this side it is 1 by 60 8 minus 9 minus 1 by 6. I think this is correct, no? So 4 by 1 it is how much? 1 by 45. Mhm. 720. I don't know what. Just check my calculation. I doubt my calculation is correct. Just check. Okay, so it is coming roughly 137, right? Eight minus minus one, 6 minus one, 6 plus. I take 1/60 common. Just
Sir,
check what
I got 137.15. 14 actually. 14.
roughly that's fine.
Yeah,
And V is positive, it means the image will be from the right side, right?
yeah.
Now, imagine if I tell you to make this question even tougher, that this entire medium is having length only 100. So 137 is more than 100, right? So 37.14 is beyond this. So for this interface, the final image will be different because assuming the medium is extending up to infinity, this is the answer. That is, if the same water will persist, this is the answer. So what if the medium suddenly ends, abruptly ends before the answer, before the image? Then if the light ray was supposed to go here, the medium may bend like this. Or uh, so how to find this new answer? So for flat interface, we can write the the object, I mean, this image will act as the object for the second interface, and therefore we have the formula that the d apparent upon mu of observer is d real upon mu of object. So the d apparent turns out to be the mu of observer is 1 and d real is 37.14 and mu of the object is actually 4/3. So this turns out to be 3/4. So the answer will be 27 point. Let's make it 86. So final image will be from lens 127.86. So you can understand that if the light ray will suffer one more refraction, you have to write the law of refraction. Or instead of using all these things, you can stick to the same method. What is the same method? Our method is
So could you
mu
repeat the
2.
question?
See, the answer we got is with respect to what? Water, no?
Yes.
Our answer is in water, but the water is abruptly ending here, only at 100. What will happen? The light ray will suffer one more refraction. And the expected position of the image from the interface is 37.14 because the light ray is coming something like this. Understand?
Yes.
And now what will happen? You will write the formula. Which formula? The refraction mu2. Mu2 is the air by V minus mu1, which is water, by U, which is plus 37.414, equals to 0. Why 0? Because the radius of curvature is infinite for interface. Understand? So V is how much? 3 into 37.14 by 4. Which means the final image will form at 27.86 centimeter from the last refracting surface. Do you realize this?
Yes.
The lens will have two surfaces close to each other, but this surface is quite far. So it is like a case of thick lens, and therefore we have to find the actual answer. Now do you realize this?
Yes.
Imagine it looks like a banana, right?
Yes.
But actually it's a thin three lenses actually. And all are thin lens. Find focal length system. We have air on both sides.
Okay.
No, but we have three medium. So how many lenses we have here?
So
Fine.
three.
Three lenses. How many refracting surface we have?
Four.
Four. And you can see that there are two pair which are common. So the refraction surface of the okay, that's the beauty of thin lens. They are so close that okay. Anyway, so what you have to do is write the refraction formula. How many times? Four
Four.
times. And don't worry much. Like just write in sequence and add all because all intimate answer will cancel out.
So for the Snell's law we were doing when there were parallel slabs, we could just exclude everything in between. Can we do it here or no?
No, no, it's curved surface. You have to use the refraction from curved surface. And we are assuming the thin lens condition and pixel both. So there is no gaps. Thin, the entire thing is thin.
Sir, it's approximately 20. Hello.
Yeah, tell me.
Approximate answer is 20 centimeter.
Okay. So let me write down the question. The first surface will have 1 point mu 2, which is 1.6 by v1, 1 by, okay, infinity, mu 2 minus mu 1 by r1, which is how much? 10. For second surface, mu 2,
So these are the equations.
If this is the equation, we will get the right answer. This is the answer.
Check.
Roughly 26, right? This is coming, no? 26 centimeter. Okay, anyway, you can check. That's not a big deal. You can check and you can get your answer. So technically, we are very close to ending of this chapter. So there are just few concepts left. But the next lecture will have few concepts. Then we also cover the defects of vision. And I will take one more separate lecture for optical instrument, in which we study about the telescopes and microscope. Okay. With that, we complete the geometrical optics completely. Nothing will be left. Just yes.
So geometrical optics is optical instrument is another chapter in SCV, no?
Yeah, in SCV, the defects of vision is a separate chapter. Optical instrument is a separate chapter, but all are part of ray optics.
So there are like small chapters.
Yeah, they are very small. One lecture each. Okay.
Okay,
So I will cover both chapter. Again, I'll try to keep your lecture tomorrow, if possible tomorrow. Then this week I'll finish everything. Okay.
yes, sir.
So so that you can have the completion of optics, which is a huge chapter actually. It's roughly 13, 14 lecture chapter in fact. But it is an easy chapter. Somewhat you need to know some theory actually. I mean, for good with the theoretical understanding, if you know the ray diagram really well, you won't find this chapter difficult at all. And if you know the do's and don'ts, like today we discussed like when to apply, when not to apply. So those things are very crucial. Okay. So we'll see all these things in the next lecture as a separate idea. So this answer you remember because I will solve this in a different fashion in the next okay. And next lecture.
Sir, when is the next lecture?
Hopefully tomorrow or day after. I'll mention.
Okay, sir.
He will communicate with you.
Sir, and when is the next conductance? Like,
Capacitor is on Sunday.
okay, yes, sir.
And anyway, I have uploaded the magnetism chapter. So magnetism is a separate chapter. If you want, you can start studying magnetism.
So I wanted to ask, will you be teaching magnetism in that batch also?
Hopefully, I will take only numericals. Like all the theory, I will expect that you will be watching those lectures, and I'll try to only solve the 44 years of question. That's it.
So after capacitors, you will start current electricity.
Yeah.
And then after that,
After that, magnetism, you have to watch from video. We'll practice in the lecture. Then I will teach EMI just to save time. So
okay.
magnetism, once you practice, we can finish in 2 lectures. in maths, and by at the end of 2 lectures, we can go directly to EMI, the electromagnetic induction, and AC.
Sure, how many chapters are left then?
Up to AC only, and AC and modern physics. That's it.
Yeah,
Sir,
okay.
and then after our optics over here, then you won't teach here anything.
I'm planning to take a web optics. Hopefully.
Okay.
Yeah. So diffraction and web optics will be helpful too. And because I will be teaching your batch, so of course they will not learn those chapters. So that will be in your batch only. So we'll try to put everything in detail so that everyone can watch and understand. Do attend the lecture of web optics.
Yes.
Yes, sir. So please will you send the link of where you upload that
Yeah, yeah,
lecture?
sure, sure. I think I have shared the link.
Can you share us?
Oh yes, sir. Yes, sir.
Yeah, I have shared. You can share with others if you don't have. Okay, bye and
Okay.
take care.